Hello, and thank you for coming. My name is Alex. I am a software engineer in the Google Cloud Client Libraries team. I'll tell you how my team switched from using multiple Docker containers to a Bazel workflow. Let me start with a short description of our workflow. We develop code generators that produce hundreds of client libraries for various Google Cloud APIs in 7 programming languages. The source code of all the libraries is stored on GitHub, and from there we publish them to the corresponding package managers, such as npm for TypeScript, PyPy for Python, and so on. Today we are going to talk about the generation part of the workflow. There is a separate code generator for each of the 7 languages we support. Each generator takes an API definition as an input, and those definitions are in protocol buffers format, published on GitHub. So technically, each client library generator is a plugin for Proto-C, the protobuf compiler. I won't go deep into the client library specifics here. Please check out aap.dev for information about our standards for proto definitions and aap.dev/client libraries for the client library generators. It's important to know that each generator is written in the language it generates. That is, the Java client library generator is written in Java, the TypeScript generator is written in TypeScript, and so on. The main reason for that is that we want the language communities to be able to contribute to the generators. So we have 7 similar but separate generators, and each of them requires the setup for the corresponding language to work. So we needed to have 7 language environments for generating client libraries, so Docker was an obvious choice. So we had a Docker image for TypeScript generator that had Node.js inside, and then we had a Docker image for Python generator, and so on for all 7 languages. And we had a spec that defined how all these images should behave. And it all worked, but the complexity of the infrastructure was just a little bit higher than we wanted. First of all, dependencies and generator updates. With Docker images, it's not only a Docker file update, but you also need to rebuild and publish the images. Then everyone who needs to build client libraries needs to have Docker installed, which is an extra dependency on the developers' machines, and not all our developers actually use Docker a lot. And using this setup and continuous integration requires a lot of plumbing, and there are a lot of moving parts. Having reproducible builds is hard because, having that many images, even if you carefully tag them, something will go wrong if you try to rebuild some older code. And finally, running a generator by running Docker image is pretty hard. You need to pass a lot of parameters like mount, input, and output directories. So we had a lot of shell scripts that set various parameters for each API we built, and they basically acted as wrappers for the Docker run command. And so to make a long story short, it was pretty complicated. So Docker images helped us set up the workflow in 7 languages, but it became obvious that we needed something else. So we realized that we needed a build system that could execute Proto-C plugins that are written in various languages, that could keep track of all the language runtimes and dependencies, could generate reproducible builds, and could be run locally by engineers without a lot of setup. So as you probably guessed, we switched to Bazel. Now let me talk a little bit about our current setup on Bazel. We don't use the per language Docker images anymore. We still use Docker here and there, especially in continuous integration jobs. But we have just one image with Bazel inside, and the jobs just run Bazel to build everything. As I mentioned earlier, we have all our input proto files published in a GitHub repository. So this repository became a Bazel workspace. The workspace file is the single place where we can control the generator versions that we use and all the common dependencies, such as the protobuf library. The client library generator for each language became a Bazel binary. We have generators written in 7 languages, so the full build of the workspace loads and runs the code written in all those 7 languages. Changing the generator to become Bazel binaries was easier for some languages and harder for some other languages. Like for example, for Java, Python, and Go, it was pretty straightforward to do since we have Java binary, Py binary, and Go binary rules. For TypeScript, it was a little bit less straightforward. Some code needed to be changed because it relied on relative file locations, like the existence of the build folder, and it all has changed after moving to Bazel. Also, there were some issues with the Protobuf.js library that wanted to install its dependencies by calling npm install directly. So we needed to make some minor changes here and there to make it work. And the other three languages we support are C Sharp, Ruby, and PHP. We are aware that there are implementations of C Sharp rules, Ruby rules, and PHP rules. For various reasons, we weren't able to use the existing rules, so our team members implemented our own C Sharp binary, Ruby binary, and PHP binary rules, and these rules can be found in the source repository of the corresponding generators. Now let's talk about the generator dependencies. Each generator defines its dependencies in macros that are defined in repositories.bzl. Here is an example from the TypeScript generator that loads Node.js rules. Generators may have common dependencies such as protobuf library, so we use maybe to make sure we only load each dependency once. Now, since all generators live in the GitHub repositories, they need to be loaded from the main workspace file as dependencies. This is an example of loading the TypeScript generator from the workspace file. We have the same HTTP archive rule for all the generators. So after we loaded each generator, we need to use the macro to load the dependencies of each generator. That way, all the individual dependencies are managed within the generator repositories, and in the main workspace file, we just load the generators using their specific versions. We also need to execute some extra actions like installing dependencies, like the yarn install rule here. Now let's take a look at the actual rules that we use for building all client libraries. Each version of the proto definitions for each API lives in its own directory. So here we have two versions, v1 and v1p1 beta 1 of the speech to text API protos. And each version has its own build file that lists generator targets for each language. So we have a separate tool that can generate these build files for new APIs. This is a snippet taken from the build file for the Google Cloud speech-to-text API. This snippet defines a TypeScript client library target. Here, this GAPIC part of the rule name is a name we use for Google Cloud client library generators. Each generator implements its own rules that generate and pack client libraries, so we have some Starlark code in every generator. If we look at the parameters for the rule, we can see some parameters that we need to pass to the generator along with the protocol buffer definitions. Previously, when we used Docker, these parameters were stored in the shell scripts, and now we store all these parameters in the build files. They are the source of truth for all configuration for the generators. So to summarize, at this moment, we have an automatically generated build file for each API, and each build file has targets for all versions. Uh, Engineers can either build a specific target, like build a speech API client library for Node.js, like the first line here, or they could use the star syntax or a triple dot syntax to build multiple client libraries for multiple APIs. That's what we normally do in our continuous integration tasks. The build of library in a clean workspace is in fact pretty fast. On my laptop, it takes a little bit longer than 2 minutes to build one library. That's when I start from a clean workspace with no cache. So basically downloading and building all the dependencies, protobuf library and such. Subsequent builds are of course almost instant. In total, at this moment, we have about 300 build files in the workspace, and rebuilding the whole workspace without a cache takes about 20 minutes in continuous integration. Now let me talk briefly about our next task that we are working on. A big improvement to our workflow will be to compile the generated client library code and run the generated unit tests right after the build. So you could say Bazel test and immediately test the generated library. We already have this for Java, but not for other languages at this time. So we are working on adding that. So currently, we run the unit tests for the generated code separately in continuous integration, and moving this step to Bazel will simplify our workflow even further. Everything I described in this talk is open source, and it's all available on GitHub. The main repository with protobuf definitions and Bazel build files is github.com/Google APIs/Google APIs. And the generator and the rules are all in the corresponding language repositories, copy generator language. So please feel free to take a look at how this works, and we'll appreciate any questions or feedback. Last but not least, I wanted to acknowledge the work of all the team members who worked on this project. Their names are listed on this slide. This was a big transition, so thank you folks for making this happen. And that's it. Thank you for watching.